Hello, peoples. This video is to help you with a general problem-solving strategy for work and energy and how to set up these problems. I chose a problem that was reasonably difficult, but nothing too easy, nothing too hard. And the scenario is basically of something sliding down an incline and there's some friction. That's the scenario. All right. After you've read this problem, when it comes to work and energy, I do suggest drawing a picture. It might help you to visualize what's going on. And in this case, it is an incline that is 5 meters long. So I'm just going to draw this out really quick. We got an object whose mass is not given. Oh my goodness, we don't know the mass. What to do? The angle of the incline is 15 degrees. How nice. And the length is 5 meters long. And it starts from rest, so you may want to label that the initial velocity is 0. If you'd like to do that, the initial velocity is 0. The final velocity is actually given in this problem. The final velocity is 2 meters per second. I'm going to write that down. And when it comes to work and energy, you have to define some zero reference height, and I tend to choose the lowest part of the story as my zero height. So for me, that's right here, height equals 0, but that means that it's starting at a height above 0. This height is basically right triangle math. I'm going to draw this on the side. I know we did this in class, but as a reminder, if I can draw it, my computer's lagging today. This is the distance of the incline or length of the incline. This is the height, and this is the angle of the incline. The trig function that relates these three, the opposite, the hypotenuse, and the angle, is sine theta, which is opposite over the hypotenuse. So the height is actually the distance or length of the incline, sine theta. I always do this when I draw my picture. I like to do that right away. Again, that the height is d sine theta. In this case, 5 meters times sine 15. And we get a height of 1.29 meters. I like to do that ahead of time. And if you don't know what this length is, this 5 meters, and you're actually solving for it, that's fine. In that case, it would just be d sine 15, and sine 15 is a decimal, so you get decimal times a distance d. It's fine, but you should do that. Just because you don't know the distance doesn't mean anything. All right, your next step is to write out the work-energy theorem, which is the initial kinetic energy plus the initial potential energy due to gravity. AP, if you're watching this, you know that that is referenced as UG, but it's the same thing. Any work done by an external force, final kinetic energy, and final gravitational potential energy. In a little bit more detail at the end of this will be reviewed, but in how to cross off what energies don't exist, what questions to ask. And it'll be a little bit more written out for you. But here, kinetic energy is energy of motion. So the question is, initially, is it moving, yes or no? Well, no. I'm going to cross it off. Initially, that's what the I stands for here, is the object above height 0, because potential energy is based on height. So in the beginning, yes, it is. I'm going to leave that there. Are there forces doing work? Usually forces that do work would be a rope, somebody pushing or pulling, an applied force, definitely friction. Usually not gravity, unless it's AP, and we're talking about the Earth is not part of the system, and usually not the normal force. So there is friction. We're going to leave the work in there. Is it moving in the end? Yep. Kinetic energy is based on motion. Is it above height 0? No. Cross that out. After this, all we've done is identify what energies exist and don't exist in our story. That's it. After that, we pull down the math. The math would be mg h initial plus the work done by friction. Okay, I'm going to take this a little bit in detail here. The work done by friction would be the force of friction acting for a distance delta d, and the angle between the force applied and the direction it's moving is 180. And I can promise you, for all the problems we do, that the force will always be opposite the direction it's moving, the force of friction. So it'll always be cosine 180. which happens to be -1. So if you just want to make the work done by friction negative right from the start and not write cosine 180, I'm good with that. Now, friction, as you know, is mu Fn. Don't forget the distance. Don't forget the negative here. And the normal force on an incline, if you know this already, is equal to the force of gravity in the y, which would be mg cosine angle of incline, mg cosine theta. There's your normal. That is the normal force acting over a distance. Don't forget the delta d. Everybody does. Okay. If you're not sure where this mg cosine theta comes from, please see your notes on the first couple days of inclines, or the first couple days of inclines, or just the first video that I have available on my website for inclines to show you where that mg cosine theta is coming from. All right, and then afterwards, kinetic energy is 1/2 m. Oops, I put 1 over m. This video will not be edited. 1/2 mv squared, final velocity squared. Okay, terrific. So here are our three terms. They're kind of a little haphazard here. And I think some of you know what's going to happen. Is there an m in every term? And the answer is yes. So the mass does divide out. There has to be an m in every term. Also, in this problem, the mass was not provided. It's not even mentioned. You're not asked to solve for it. So it's probably obvious that the mass will divide out. But be careful. Some people just cross out masses like, oh yeah, just cross out the mass. You can't do that. What if you're solving for it, crazy person? Slow down. All right, here we go. Subbing in some numbers now. We've got 9.8 meters per second squared times the height, which I solved for earlier, which is 1.29 meters. Minus, because the work done by friction will be negative, mu, which we don't know, 9.8 meters per second squared, cosine 15, don't forget the distance, which is 5 meters, equals 1/2 the final velocity squared. Final velocity was 2 squared. Here's the thing. It may be tempting to immediately solve for mu, but these problems are going to get pretty complex. And if you do that and you go from here to an answer and I can't figure out what it is, it's really hard to figure out where you make your mistake. So what I'm asking you to do is to do each little section here, like the 9.8 times the 1.92. I can do that right away. That's going to be 12.6 meters squared per second squared. Those are the units. Minus, and then if I do 9.8 cosine 15 times 5, I get 47.3 meters squared per second squared times mu, and then 1/2 4 that's pretty easy. I can do that one in my head. 2 meters squared per second squared. Now, if you go right from here to solving for the coefficient of friction, I'm okay with that. This is simple math. But if you did it originally just from this equation, I don't know what you did. Did you forget the half? Did you forget the square? Did you lose the distance? Like, I don't know. There's so many mistakes. So take your time, write it out to here, and then solve for mu. And you would get that mu is equal to, I wrote it down somewhere, and now I can't find it, and this video will not be edited. So you must suffer as I do this. Sorry about that. 0.224. That is your answer. Okay, so that was a basic problem, and I'd like to basically review, if you wouldn't mind, some of the important aspects of work and energy problem solving. Oh, you must get tired of hearing this voice. All right. So this is my problem solving strategy for you, designed especially for you. Draw a picture if it helps, and I would label as much as you can: initial velocities, final velocities, heights of 0. If it's an incline, I strongly suggest, I'm going to write this right here, right now. Don't forget that if it's an incline, this little picture, why is it not drawing? There it is. Oh, we may have to edit. Oh, we don't have to edit. Yay. It's not making me happy here. The distance and the height and theta. We get that height is d sine theta. And again, if you don't know what the distance is, no big deal. You just write h is d sine theta. All right, now my triangle disappeared. That's just amazing. My incline has disappeared. Let's try that again. Okay. Anyway, write out the work energy theorem and use the setup use this to set up the appropriate math. Focus on initial and final conditions. We're going to be doing sort of multi-part problems, but they're no longer multi-part. You just care about the beginning and final conditions. What energy do you start with? What energy do you end with? And is there any work done in between? So this is what I was talking about in more detail, this work energy theorem. Every year, people are like, I just don't understand what to cross out and what not to. Kinetic energy, starting with the one on the left, is energy based on motion because it's 1/2 mv squared, velocity. So initially, is it moving? Yes or no? If the answer is no, cross it off. And then you're like, yeah, but it's above height. I don't care. Is it moving? Yes or no? These are simple questions. Don't add anything to these questions. For initial potential energy, is the object above or possibly below height 0? If the answer is yes, leave it. If the answer is no, cross it off. And some people are like, yeah, but it's above height 0, but it's not moving. So who cares if it's moving? It's mgh. Where do you see velocity in that equation? I see h. Is h 0 or not? That is the question. Work. Are there any external forces doing work, like a friction, applied force, tension, that change the energy of the object? Usually gravity does not do that unless we're in AP or the normal force. So if the answer is no, cross it off. If the answer is yes, like in this problem with friction, leave it there. And then for the end, final kinetic energy, is it moving in the end, yes or no? And final potential, is it above height 0 in the end, yes or no? Or below. And as a reminder, work is force times distance times the angle between the force and the distance. Basically, which way is it moving? Which way is the force being applied that's doing the work? And I promise you that friction will almost always, but pretty much always, be 180. Like it'll move to the right and friction will act left to try and remove energy from the system. So it'll always be cosine 180, or friction will always do negative work. And then afterwards, once you've crossed out all your energies that don't exist, fill in the math and solve, basically. But I ask you to chunk it where you do like, okay, let's calculate kinetic energy. Let's calculate potential energy and like work your way down. Don't just set up one giant equation and solve. Take the extra step to do each chunk. But other than that, this has been a rather long video. I hope it was helpful because that was its purpose. And I'd give this one roughly 3 out of 5 stars, and I wouldn't change a thing.